Welcome to Developing Graphics Frameworks with Python and OpenGL, Part 16, Linear Transformations and Matrices. In the previous video, we learned about vectors and some operations on vectors, and two particularly important ones. We learned about vector addition and scalar multiplication. In this video, we're going to learn about vector functions, that is, functions which take a vector as input and a vector as output. We're going to talk about specifically nice vector functions called linear transformations that interact well with vector addition and scalar multiplication, and see how that very naturally leads us to a concept called a matrix. So to begin, vector functions. Our goal is to create functions that will transform sets of points or vectors in certain geometric ways. Now, there's lots of different ways we could write a vector function, right? So I'll usually use a capital letter for the function, and the input could be a point, and then the output could be a point. In this case, we typically drop the interior set of parentheses. More frequently, we might see this notation, a function which takes a vector as input and gives a vector as output. In mathematics, it's more traditional to write the vectors as columns. So I have the column vector, v1, v2, as input, and outputs, the vector w1, w2. So that's the way we would write a vector function. And there's lots of different vector functions in the world. Any algebraic expression you write could be a vector function. So for example, you could have the zero function, which takes any input vector and always gives you the vector of all zeros as output. You could have the identity function, which takes as an input any vector and gives as output that exact same vector. Or you could have a useless function, f of v1, v2. I'm not even going to read this vector. So there can be very simple vector functions, very complex vector functions. The goal is to find something in between, right? A moderate vector function, which is still capable of expressing all the different geometric transformations we're going to be interested in. And it turns out those functions are going to satisfy two special properties. A function, a vector function, is called a linear function or a linear transformation if it satisfies these two properties. First, f of a scalar times a vector is equal to the scalar times f of the vector. It's almost like you can factor out scalars. Also, f of vector v plus vector w is equal to f of vector v plus f of vector w. In other words, it kind of looks like we can break up a function over addition. Any function which possesses these two properties we'll call a linear function. And it turns out you'll see this set of properties in all sorts of areas of mathematics. For example, if you've had calculus, this might look like some derivative or integral properties, where instead of f, you might be doing a derivative or calculating an integral, and instead of vectors, you'd be working with functions. These properties are very common throughout mathematics. Now, it turns out that any vector function with these properties is really amazing to work with. So, you might recall, hopefully from the previous video, the basis vectors I and j. I is the vector 1, 0, and j is the vector 0, 1. And last time we talked about the fact that you could write any vector v, say with components x and y, as a linear combination of these two vectors. You could write it as x times I plus y times j. And it turns out one of the reasons linear functions are so special is that you can calculate the value of a linear function if you know the values of f of I and f of j, even if the general formula is not given. For example, let's say you have a linear function f, and you know that f of I equals 1, 2, and f of j equals 3, 1. Just based on the fact that it's a linear function, it's possible to calculate the value of, for example, f of 4, 5. Now, how can we calculate that? Well, it just comes from the linearity properties. Right, to start, with f of 4, 5, we'd start off by breaking up 4, 5 as a sum, 4, 0, and 0, 5. And we know that because the function f is linear, we could write that as this sum. Next, we would factor out a constant number from each of these vectors. And once again, using the fact that the function f is linear, we can factor out these constants. Now, 1, 0 is really the basis vector I, and 0, 1 is really the basis vector j. And we know the value of f of I, and we know the value of f of j. So we can substitute those in, perform the scalar multiplication, and then perform the vector addition. So we know the value of that. And there was nothing special about the vector 4, 5. We could replace that with an arbitrary vector, say a vector xy, like so. And this would actually give us the general formula. The steps are identical. We're just replacing that specific example with a more general case of x and y. Again, we split it up using vector addition and use properties of linear functions. Then we further simplify it using scalar multiplication. And since we know the particular values of f of I and f of j in this case, and we have a general formula for this function. That's pretty cool. In fact, we can become even more general for this. Right? We actually now know that every linear function is basically going to have this form. Imagine for a moment that the vector 1, 2, the value of f of I, instead of the numbers 1 and 2, let's say those are the variables a and c. And let's say the value of f of j, instead of being the specific case of 3 and 1, let's say those are replaced by the variables b and d. Then we know what the general form of a linear function is going to be. If, by the exact same mathematical derivation, if f of I is equal to the vector ac, and f of j is equal to the vector bd, I won't bore you with the mathematical derivation again, but it turns out the formula has to look like this. So any linear function, its formula can be written like so. Also, it's really nice that there's a good geometric interpretation of linear functions. Right? In the last video, when we talked about vector operations, we were specifically interested in vector operations that had a nice geometric interpretation. Here, we're fortunate that linear functions also have a nice geometric interpretation. To see what they do, to see how they transform points, let's consider the following. On the left side of this diagram, I have a square. Right? That consists of the set of points whose coordinates are between 0 and 1 on the x-axis and between 0 and 1 on the y-axis. So that set of points, that square, which I'll denote with the letter S, you can think of that set of points, u comma v, as the points which can be written in this form, u times I plus v times j, where u could be any value between 0 and 1, and v could be any value between 0 and 1. Now remember, if f is a linear transformation, so it satisfies those two special properties, if you know that f of I is equal to the vector m, and f of j is equal to the vector n, then you actually know what happens to this square s. It turns this square into this parallelogram, where the vector I gets sent to the vector m. That's kind of the bottom edge of the parallelogram over here. And the left edge, j, is mapped to this vector n. And it turns out that every point within this square can be written as some combination of I and j. Because the function f is a linear transformation, f of u times I plus v times j, well, we can break that apart with the vector addition and the scalar multiplication. replace f of I by m, replace f of j by n. Right? So f takes every point inside the square and maps it, or transforms it, into a combination of m and n. And once again, the values of u and v are between 0 and 1, which means that the points inside the square must map to the points inside this parallelogram. Linear transformations turn squares into some sort of parallelograms. All right, so there's some nice geometry going on. Now let's rewrite this a little bit. So if you were to rewrite a linear transformation using that column vector form, it's going to look something like this. Right? F of the vector xy is equal to this. Now we really like to think of the vector xy as being operated on by the set of numbers a, b, c, and d. And so there's a mathematical notation that was invented. Just take the numbers a, b, and c and group them into a rectangular grid or rectangular array, which is called a matrix. So that expression can be rewritten like so. And that means that the product of a vector and matrix must be defined in this way. So the matrix ABCD times the vector xy is equal to the vector ax plus by is the first component, and cx plus dy is the second component. And that's how the matrix vector product is defined. And so if you want to do some calculations with this, it's not too bad. It's a fair amount of arithmetic. So for example, let's say I have the matrix 2, 3, 4, 1. Right? And if I want to calculate, say, f of 5, 6, right, how does the function f transform the vector 5, 6? Well, we just use that formula. We arrange the numbers as follows. We do the calculation, and we see that that function would transform the vector 5, 6 into the vector 28, 26. Similarly, here's another calculation. If you want to see how the function f transforms the vector negative 3, 1, again, you just perform a similar calculation. And so linear transformations, they transform vectors into other vectors. Now, just as before we've talked about vector notation, we should say a little bit about matrix notation. Generally, we'll represent a matrix with a bold uppercase letter, and we'll enclose the values in a set of square brackets. Unlike a vector, which is kind of a list of numbers where we use single subscripts, for a matrix, since it's a grid of numbers, we'll often use double subscripts to indicate each component of the matrix. And those subscripts will indicate the position of an entry. So for example, if you have a matrix with the entry A12, that means this component, this value, occurs in row 1 and column 2 of that matrix. Or in general, A with a double subscript MN, AMN, refers to the entry in row M and column N of a matrix. So if I have a matrix with 2 rows and 2 columns, then I would write the entries of that matrix in this form. Now, in a lot of our applications, we're going to want to apply a bunch of different transformations. We might want to translate an object and then rotate it, then maybe translate it again. And so we also need a way to combine linear transformations. So here's kind of the big question. Let's say you have 2 different transformations and they each have an associated matrix. Right? We've just learned that every linear transformation has a corresponding matrix. If you were to combine those transformations, how could you calculate a single matrix representing that combination? Now, the sentence is a little bit hard to make sense out of. It's a little bit easier to understand algebraically. Let's say you're given two transformations. Let's say the transformation F consists of multiplying a vector V by matrix A, and you have a second transformation, G, which transforms a vector V, multiplying it by a matrix B. So what we'd like to do is find a transformation which represents the combination of F and G. In other words, we want to find a new transformation H and its associated matrix C, such that this new transformation H has the same effect as the transformation G followed by the transformation F. Right? In other words, we want these two quantities to be equal for all vectors V. And in that case, we would write the matrix C equals the matrix A times B, and that's actually how matrix multiplication is defined. Right? It's not a definition that somebody made up. It has to be defined in a certain way so that composition of transformations is consistent. And so, really, it's a bunch of algebra. The strategy is, well, if you want these two things to be equal, calculate both sides, set them equal to each other, and then set the coefficients of x and y on both sides equal. So if you have the matrix C times the vector V, you'll end up with this quantity. If you have the vector V and then you multiply by the matrix B and then multiply by A, well, that's a lot of algebra. But at the end, you have basically the same format. The first component is something times x plus something times y. The second component is also something times x plus something times y. Right, so the coefficients of x and y in the first component have to correspond to these values of the matrix C. And the coefficients of x and y in the second component down here must correspond to these coefficients. Right, so at the end of the day, this is the formula for matrix multiplication. It's a little bit complicated to remember just on its own. The easiest way to remember it is actually with another vector operation. There's something called the dot product. The dot product operation is another operation which comes in very handy when working with vectors. Here it's going to help us remember the formula for matrix multiplication. The formula is defined as follows. Given two vectors, u and v, with components u1, u2, and v1, v2, the dot product, which is typically indicated with a very large dot to distinguish it from kind of a normal multiplication size dot, this is defined as the product of the first components plus the product of the second components. Right? And the result is, actually it's not a vector, it's just a number. Now, the reason this is very useful is each one of these entries in the matrix product has this basic form. So the way you can remember this is take your first matrix and partition it into two rows, right? And think of each row as a vector. For the second matrix, partition it into columns and think of each column as a vector. And then the idea is that if you have entry CMN of the matrix C, in other words, the entry in row M and column N, you can calculate that with the dot product of row M from the first matrix and column N in the second matrix. So for example, the entry C11, which occurs in row 1 and column 1, is the dot product of row 1 from the first matrix and column 1 from the second matrix. The entry C12 in the product, that is row 1 in column 2, you can calculate as the dot product of row 1 from the first matrix and column 2 of the second matrix, and so on for the other entries. And so this might help you remember this formula. Now, just as an example, we wouldn't want to do a formula without an example. Let's say we have these two matrices. The first matrix is 2, 3, 4, 5, and let's say I want to multiply that by 9, 8, 7, 6. Right? Remember this nice little mnemonic. I want to partition the first matrix into two rows. So think of it as the vectors 2, 3, and 4, 5. And the second matrix, I want to partition that into columns. So think of that as the vectors 9, 7, and 8, 6. You'll notice that when we do the matrix product, right, we have these 4 different dot products, row 1 and column 1, row 1 and column 2, row 2 and column 1, row 2 and column 2. And then we just have to calculate each one of these dot products using the dot product formula. So for example, 2, 3, dot 9, 7 is going to be the product of the first two numbers plus the product of the second two numbers. Right, so 2 times 9 plus 3 times 7. It's going to be 18 plus 21, and that will give us 39. And we go through a similar calculation for each of the remaining dot products, and that gives us this matrix. And so, in general, this does become very tedious after a while, and so luckily in Python, there's a really great library called NumPy, which does a lot of the matrix calculations for us. So we're going to be relying on that matrix library quite heavily in what happens. And so that's how matrices work. That's where they come from. They come from they kind of naturally arise from considering nice linear transformations. And everything we've done so far has to do with 2x2 matrices. In the next video, we'll talk a little bit about how this generalizes to larger matrices. So for example, vectors with 3 entries and 3x3 matrices, or vectors with 4 entries and 4x4 matrices. And that's about as large as we need to go for doing computer graphics. Thanks for listening.